podcast. This is Mr. White.
Mr. Johnson.
And today we're going to do Newton's third law of motion. We've done the first law. Objects in motion stay in motion.
Objects at rest stay at rest.
Unless acted upon by a force. We've done the second law, which is the math one. Force equals mass times acceleration. So, Mr. Johnson, what is Newton's third law?
Well, the third law is that there's two forces acting on an object.
Okay.
Both opposing each other.
Ooh. Okay, so math-wise, I would write this. And oppose opposite, so I can get away with a negative sign. So for every action, there is an equal but opposite reaction.
Right.
That's an important one of Newton's laws. So let's see. I'm sitting on this chair right now. What must be happening?
Well, one, you're pushing down on the chair.
Okay.
And the chair is pushing up on you.
Excellent. So sometimes we refer to these as action-reaction pairs. Pairs is a key word, meaning that forces don't exist by themselves.
No.
There must be something else acting as well.
Always need two.
Always need two. So if I were standing on the ground, okay, I'm pushing down, the ground's pushing up.
Correct.
What if the ground couldn't push up? What would happen to me?
You'd keep going down.
I'd keep going down. I'd fall through the ground.
Right.
So when you're walking on a leaky roof, all right, and you step on that leaky roof, you put your foot through it, it couldn't supply an equal but opposite force to your stepping.
You go right through it.
And that's all that's happening there. It's not. It's really not that complicated, to be honest with you, but a different idea nonetheless.
They're kind of like quicksand?
Kind of like quicksand, yeah. So what we're going to introduce to help us keep track of this is called a free body diagram. Now, I'm terrible at drawing, in case you haven't noticed.
You've done well so far.
Yeah. And so a free body diagram is nice because a dot will represent all of our objects, whether it's a person or a car or a chair or a feather. It doesn't really matter. And I just draw all of my forces off of this. So, for example, if I were to free body diagram me standing on the ground, then we've got me, which is my weight. So this is sometimes called F sub g, or the force due to gravity, or my weight. And the ground force is pushing up, and we call that the normal force. And way back when, I took a geometry class, and I remember my geometry teacher, who still teaches in this building. We'll let you guess who that. Let them guess who that is later. She told me.
Oh, you gave it away.
Did I? She told me that normal meant perpendicular. So the normal force is always perpendicular to the surface. So for flat ground, normal or perpendicular would point straight up, and it has to be opposite of the weight.
Okay.
Okay. So in the investigation, I took great joy in watching you guys with the force sensors, because we gave some instructions that said hook two force sensors together and pull on them until the force reading is not only different, but one is double the other. It was very specific.
I'm actually surprised we didn't break any.
Right. We didn't break any force sensors. That's good. So what would happen here is if this guy read 10 newtons, what were they discovering?
Well, the other guy had to read 10 newtons.
Yeah. And if they pulled really hard and they discovered that 100 newtons on the left meant
100 on the right.
And I want you to remember, of course, who free body diagrammed this, that these are in opposite directions. You can't get a force on here if you're pushing them towards each other. That's not the way these force sensors are built. And so as a result, what you notice, of course, is, yikes, I can't make this happen. And lots of students said, hey, this is impossible. How did you respond to that comment, Mr. Johnson?
I just smiled. And
Yeah.
grinned. Took a lot of enjoyment out of that. 'Cause
I did.
They got it.
They got it. The moment you say it's impossible, you've got it. Now, you're frustrated as a student, of course, because the directions say that this is possible. And, well, of course, we're like, well,
It's not.
it's not. We had you do an experiment to disprove this idea of non-equal but opposite forces.
Plus, we need our fun too.
Sure, sure. And we also did these experiments when we were sitting in the rolling chairs, right? And then we pushed off of other students, right?
Now, I gotta believe there are certain chairs that do this a lot better. The chairs I had, they didn't really work as well as the ones you have in your room.
Yeah, I borrowed some. And so we just had them. We had them sit on these rolling chairs and push off of each other.
Sure, you're not an artist?
I'm sure. Yeah, that's
Pretty good.
pretty good for stick people.
And it's abstract.
And if we were to free body diagram this, what could we say? We're pushing each other. Maybe we're different masses. Maybe we push with a different amount of force or different amount of oomph. But I said something there that I can't say. I may be pushing and you may be pushing, and we may have different abilities, but the fact that we're pushing on each other means that the force has to be not only equal, but
Opposite.
And what we notice, okay, is that the big mass and the little mass, the little mass goes far, right? The big mass doesn't go far, and that's a property, of course, of inertia. The more mass, the more inertia, the greater the tendency to sit there. So the guy that's bigger, all right, he is not going to go as far because it's going to take a larger force, which wasn't applied, to make him go farther. And that larger force would have made the tinier mass go even farther still.
But he still would have gone somewhere.
Somewhere.
Right.
What if both guys had the same mass? Theoretically, how far does each go?
Well, if you take away friction, they would just go the same length.
Right. They'd go the same forever.
Mm-hmm.
Right? Even with friction, they would just go the same distance. So we got to experiment with that a little bit. And the last thing I found fascinating that we did in class, I had my students bridge the chairs with a meter stick.
Oh, use the chairs.
Right? And we noticed, and I'm trying to draw this in there, that when I put big heavy weight on there, what did we notice?
The meter stick starts to bow.
It starts to bow. So flexibility is something that happens.
Mm-hmm.
Why didn't the meter stick break?
Well, I think the reason why it didn't break is because it's still applying a force to the actual weight.
How much force?
Opposite and equal to the weight itself pushing down.
Right, so the weight would be down, and the meter stick force would be straight up, equal but opposite. What happens when the meter stick can't supply this upward force?
Well, one would either slide off the chair or it would break.
It would break, yeah. Do you think the ground does this when we walk on it at the microscopic level?
I think so.
Yeah, it does. We can't see it or measure it. I doubt we have enough digits on our calculator to calculate it.
Right.
But this is what matter at the fundamental microscopic level has to do. You're pushing down on it. In order for it to push back, there's going to have to be some give and some take. That's the third law. We've now covered all three of Newton's laws of motion. And just to review those, first, second, third, we just did the third. Forces come in pairs. They must be equal but opposite to each other. F equals ma. In order to calculate the force, you multiply the mass times the acceleration. And the first law, stuff will do what it's doing until a force acts on it. Right? So if you've got a lazy brother or sister sitting at home, sitting there doing nothing, they're going to continue to sit there doing nothing until they apply a force with their legs to get up out of the chair.
Yeah.
Right? And that's inertia, and here we got calculations of force, and here we've got the third law.
So I got to ask, since you know, you're the big physics guy, and I do chemistry mostly. Is that what George Lucas meant in Star Wars when he said force? He's talking about mass and acceleration. So may your mass and acceleration be with you.
No,
No?
I don't think so.
No.
I have seen the T-shirt. May the F equals ma be with you. I'm a nerd, but I don't even own this T-shirt. Yeah, so there is a lot that goes on there. I guess it does bring up one more point. The Earth. Let me label that.
Big circle.
Earth is big.
Mm-hmm.
We're small. We stay close to the Earth. Why?
Well, gravity.
Because of the Earth's gravity, right? It keeps us firmly planted. The Earth has gravity because it has mass. Is that true?
Absolutely.
Okay. Do we have mass as a people?
Yes.
So, do I have gravity?
I would think so.
Yeah, we do have gravity. And as a matter of fact, the amount of gravity I feel from the Earth has to be what?
The same.
The same amount of gravity that the Earth feels from me.
Wow.
So when I jump up off the ground, here, be ready for your mind to be blown. We would all say that the Earth pulls me down. Is that true?
Yeah.
That's true. Now, here's the mind bender. If that's true, then I must, in just a tiny way, be pulling the Earth up towards me. I could never visualize it. I could never record it. I could never develop an experiment to see it. But I bet I could calculate it. That's the third law, right?
Yeah.
Equal but opposite. Earth pulls on me, I pull on it.
And you got mad hops, too.
Yeah, sure. All right, so I think that covers it.
That covers
Signing
it.
off, this is Mr. White.
And Mr. Johnson.